System Design a Rideshare app. Hi guys, my name is Manish Kumar and in today's session we will create system design of a rideshare application like Uber. The interesting part in today's session will be we will learn about Geo Sharding and Geo Event Cluster. So without any delay, let's start the session and see you in the session.
Hi friends, so today we will make system design of rideshare like Uber. So without wasting time, let's jump to step 1, and step 1 is to record the functional requirements. So functional requirements. So there are two user portfolio here we have. One is rider and another is driver. So for rider, functional requirement will be rider should be able to book a ride, and rider should be able to see the estimated arrival time. And we will not cover like the taxi type, what kind of cab it is, and payment method or details. We'll keep them out of scope. From driver point of view, driver should be able to see the pickup location, pickup and drop off location. So I think that is what we're gonna cover as part of this video. Out of scope, as we already talked about cab type, payment methods, these all we will keep out of scope. So we have functional requirement recorded here. Let's talk about non-functional requirement now, and we will get better understanding of the system. So NFR is a highly available system we need, because it has to be definitely fault tolerance. If user has a ride booked and he is waiting for ride and suddenly system get down, so it will definitely not going to be a good experience. User will be extremely unhappy. So this has to be highly available. Second is latency. This has to be ultra low latency. Why I am saying ultra low latency? Because user should be able to see the live cab location. And then third is scalable. It has to be highly scalable system. So let's do the capacity math, and there we will talk. So let's assume that we have 500 million user base and 20 million cabs registered in our app. And out of 500 million, let's say 100 million daily active users who are booking one ride, like 100 million daily active users booking a ride, and let's call 10 million daily active cabs. So we have 10 million daily active cabs and 100 million daily active users who are booking a ride daily. So basically the biggest thing here is how we will store the cab locations. So let's say cab sending location in every 4 seconds. So the location data per day will be 100 million users, 100 into 10 raised to power 6 per day, 24 into 60 into 15, because the location data is coming in every 4 seconds, so 15 times in a minute. So the location data, we can make certain assumption for it, like maybe the average size of the message is like 100 bytes. So this will come out, you can see if I simplify 24 into 15 into 60, maybe 10 raised to power 3 I can call it. So 10 raised to power 7 into 24 into 10 raised to power 3 into 10 raised 100 10 raised to power 2 bytes. So this is 24 terabyte data per day, the location data. So we have the per day data now. 10 million cabs in 4 seconds sending their location. This will be heavy read and write database. It has to be, because as we can see, 24 terabyte data gonna be per day, and in 10 years it will be a huge DB. So it has to be highly scalable and highly available also, fault tolerance. So I think we can use DynamoDB here. That is like key value storage, because DynamoDB will give us, like, it is highly scalable, highly available. We can implement partition also here. Lot of read replicas will be needed here. So DynamoDB will be, I think, most suitable DB here. Now if we see how much data gonna flow per second to see the throughput of the system, which will be 24 TB divided by 24 into 60 into 60 per second, data per second. And this 24 into 60 into 60, which will be around 80K around. So to round off and simplify the calculation, I will say 24 divided by 10 raised to power 5, 240 megabyte per second. So per second, there will be 240 megabyte data ingress. And so other than the location storage, we need to store metadata also. And metadata will be user information, which will be user ID, name, address, payment information, contact, and type. Type I'm saying because user could be a rider or driver. And then we have the cab information, ID, color, type, is it large SUV, mid-size SUV, and all, like, the type and other details like how much trunk space it has. And then there will be the booking information. So booking information will be definitely ID, rider who booked the ride, cab, driver, and time, pickup location, drop off location, and cost, how much we charge for this. So this will be kind of like metadata we have to store. And metadata, because as we can see, the user has, like, that is like more like each, like, user has a mapping with the cab, like who will be the driver in the cab. So cab will have a driver information also here. So this has to be, I will say, like, let's keep it a relational database and maybe SQL. 100 million booking happening in a day. So if we see, we might need a great throughput database also, because lot of write operation, read operation gonna happen in this database. So maybe we can opt Aurora MySQL also here, because as I already said, I have a good experience of SQL, so I always a little bit biased with it. But using Aurora MySQL will be, I think, also be a good option. So let's jump for the APIs. Let's a little bit talk what all different APIs we're gonna use here. So API will be user will be sending version 1.0, like booking ride, book my ride. This will be a API we will be using where ID and rider, pickup location, drop off location, time user gonna send, and there will be another, like, put for version 1.0 cab location, where ID and location and timestamp. Yeah, so I think user can book a ride and cabs can send their location. That seems like, for me, reasonable from this video point of view, but if needed we will keep adding them. So now let's jump into high level design. So we talked about rider. So rider will be sending information to the ride booking app, ride booking service, book my ride, and we already kind of talked about the databases we're going to use here. So there will be a SQL DB where the service will store the booking information, and there will be another user, driver, who will be location service, sending location, and that will be stored in Dynamo. So the user will send a request, update my location. This will get stored here, and the ride sharing will store the information here. So now how that will work? So rider will send the information to ride booking service. Ride booking service will send the information to driver that this user want to take a ride, and driver will accept the request and will send it back to rider service that yes, I'm good with it. Then rider service will notify the rider that yes, your ride is booked, and the information will get saved in the SQL database. And so the ride booking service will be having a list of servers, something like this. Server 1, server 2, all the servers are here, which are like S5, S6, and then what it will be doing, the location service, basically how it works, the Uber kind of these ride sharing app is like they divide the entire earth map into small sections and something like hexagons like this. So imagine this square is earth, so they are like breaking it into small chunks like these kind of hexagons, and let's say the rider is here. So basically what it does, the entire map is broken into these small hexagons, and each hexagon has an ID. Let's say this is 1, 2, 8, and 10. So let's assume different cars are here. They are running at certain locations in these hexagons. Something like this. So that's how the application will break the entire map into hexagon. Each hexagon has its own ID, which is kind of like, independently a piece of map. And what it will do, when this rider want to book a ride, what application does, the application draws a, so the consistent hashing here of servers, they are like, maintaining, they have ownership of different hexagon. For example, server 1 is maintaining 1 to 1, the location 1, let's say, or maybe 1 and 2 hexagons. Server 2 is maintaining 3 and 4, and similarly server 5 is, let's say, recording 5 and server. Just for your understanding, imagine this is a ring where all servers are like, allocated at equal distance. Equal distance is like ring of all the uh, these hexagon keys from 1 to 10, and by equally dividing the load on each server, these servers are placed on that ring. So now this rider who is in the hexagon 4 want to book a ride. So what it does, when this rider will book a ride, the system will draw a circle of a certain diameter around this user, and we'll see what all different cabs are available for it. So as you can see in this circle, cab in hexagon 5, in 6 and in 3 are available. So what it will do, like the server who is taking care of hexagon 4, which is here S2 will ask server 5, where is server 3, that give me ETA for this cab. It will ask server 4 that give me ETA for this cab, and 3 is itself it has, so it will just like find out the ETA. And there will be the ETA service, which is a GPS driven service, ETA service, which will be connected to this. So this server will reach out to ETA service to calculate the time it will take to reach the ride, and these all independent server will send back the ETA to ride booking service. So that this is the ETA time, and ride booking service will see the best ETA. Ride booking service will reach out to the driver, and once the driver will accept the request, it will send it back to rider. So that's how this is gonna work. Here in this design, if we run again with the functional requirement, so we can see that rider has requested to book a ride. Based upon the rider location, system identified the best suitable cab and took a confirmation from driver and sent the booking information to rider. Now here the driver ride booking service reaching out to driver, sending the pickup and drop off location, and driver accepted. So we have covered both the functional requirement here. In terms of highly available, like non-functional requirement, so what we need here, definitely we need load balancer, because all services need to be horizontally scalable. So there will be a load balancer which will be taking care of like balancing load across these services. So this will be a gateway service, and gateway service responsibility will be definitely authorization, and it will have session service where the session information will be stored. So session will be stored here, and gateway, so all driver, rider, all the users will talk to gateway, ride booking service, and these all will be stateless services. So these are horizontally scalable service. So under a load balancer can spin up more services if needed. So now if you see highly available, the system is highly available. Our services are like stateless. If one is down, another can take care of it. Latency. So here is one thing which we have not talked about, and that is the caching. So the location service here, it will be maintaining a caching. When the ride service booking or the server will ask the information about the cab, so they will reach to the caching, and the location service will store the information in caching. We can use mem cache also, but it will not be persistent, so I'll say like Reddish will be the best one here. So basically all location coming here will be stored in the Radish, and we can define the TTL for it. Like maybe we can store the recent information, the live one where it is, and all the historical will go into the database. So here these servers can reach out to live location of this from the Radish, which will help us to provide the ultra low latency in the system. And the system is scalable, as we have all services are like stateless service. So I think we have a good design here. So thank you so much, guys. So please subscribe the channel and write down in the comments if you have something specific where you want me to create a system design. I'll do that for you. And thank you so much.